tuned for that. And then without further ado, I'd like to welcome Lindsay Pease. She's at the University of Minnesota, the Extension Office, and will be our moderator for today's discussion. And before we jump in, just a quick reminder that this isn't the only seminar in the whole setup here. But we also have two more focusing on the Middle Basin and the Lower Basin on October 20th and November 3rd, respectively. You can sign up at SERA46.org, and I'll post that reminder at the end of the seminar series today as well. So, Lindsay, if you want to take it away and start introducing our speakers, I'll stop my share.
Great. Thanks, Shannon. Yeah, again, I'm Lindsay Pease, and I'm an assistant professor in the Department of Soil, Water, and Climate at the University of Minnesota, which is a good transition to our first speaker, who is a recent graduate of the Water Resource Science program. Dr. Zachary Anerud has a background in water resource science with a specialization in nutrient management and is the new agricultural coordinator at the Candiyohi Soil and Water Conservation District, where he applies his passion for sustainable agriculture and conservation. His recent research focused on optimizing nitrogen management in continuous corn systems to boost productivity while minimizing environmental losses. His work demonstrates how managing nitrogen inputs within an economic optimum range can effectively maintain crop yield and significantly reduce the environmental footprint of intensive agricultural production. This research highlights the interconnected nature of nitrogen loss and the critical need for integrated season-specific management strategies. Today, he will be speaking about dialing in the most profitable and environmentally responsible nitrogen rate. So, thanks, Zach.
Thank you. I will just share my screen. Hopefully you guys can all see that now. All right, I hope you're all having a good morning and thanks for inviting me to present today. My name is Zachary Honorud and I'll be discussing dialing in the most corn profitable and environmentally responsible nitrogen rate. As you heard, I just recently graduated from the Water Resource Science program from the University of Minnesota, and my lifetime friend and advisor is Fabian Fernandez. To introduce this study, here's a simplified nitrogen cycle diagram focused on cropping systems like corn. You don't need to memorize every arrow here, but I wanted to point out a few key things. The white boxes represent nitrogen inputs, like atmospheric deposition, manure, and fertilizer. The green boxes show nitrogen losses like through volatilization, denitrification, and leaching. The blue boxes are the chemical forms of nitrogen in the soil or atmosphere, like ammonium, nitrate, and nitrogen gas. And in the middle is the corn plant, where plant uptake ties it all together. The point here is that once nitrogen enters the system, it moves through many pathways, not all of which benefit the crop. So when we talk about managing nitrogen, we're really talking about guiding it towards the crop and away from environmental loss pathways. The overarching goal of our study was to find a balance between maximizing yield and minimizing environmental loss. To do this, we had three key objectives. First off, we wanted to evaluate agronomic responses to nitrogen rates below, at, and above our EO&R, including corn grain yield, plant total nitrogen uptake, and nitrogen use efficiency. Second, we wanted to quantify environmental nitrogen losses across the same nitrogen rates, including nitrate leaching, nitrous oxide emissions, and ammonia volatilization. Third, we wanted to integrate agronomic and environmental responses to estimate a nitrogen rate that is both profitable and environmentally responsible. In other words, we weren't just trying to find the highest yield, we wanted to identify the rate that makes the most sense when you consider productivity and sustainability. Moving on to the materials and methods, I will only go through this briefly for this presentation, and there's more details provided in my dissertation. This was a 3-year study from 21 to 2023 in continuous corn at the Southwest Research and Outreach Center in Lamberton, Minnesota. The study site is conveniently located within a quarter-mile of a weather station on site, and the soil type is a Webster clay loam. We had 5 nitrogen rate treatments ranging from 0 to 360 kilograms of nitrogen per hectare, applied in 90 kilograms of nitrogen per hectare increments, and each treatment was replicated 3 times in a randomized complete block design. Blocking was based on subsurface drainage performance from prior research to account for hydrologic differences. All plots are subsurface drained with tile installed in 1994, along with a plastic barrier around the perimeter of each plot to prevent lateral movement between plots. All plots except for the control receive pre-plant polymer-coated urea, ESN, at 90 kilograms of nitrogen per hectare, which is broadcast and incorporated with tillage. At the V6 plant stage, we applied agrotane, a urea with the urease inhibitor MBPT. The use of enhanced efficiency fertilizer, split application, and timing is based on previous research at this site. Rather than focusing on source comparisons, this study was focused on nitrogen rate, but implemented nitrogen best management practices to isolate the effect of rate under optimal management. What really makes this study unique is that we took a holistic systems approach to tracking not just yield and plant nitrogen uptake, but also soil nitrogen, ammonia volatilization, nitrous oxide emissions, and nitrate leaching simultaneously. So we weren't just asking how much yield did we get from that nitrogen, we're also asking where did the rest of the nitrogen go. For plant sampling, we took whole plant samples at around V10 and R6 plant stages to assess total above ground nitrogen uptake across the growing season. At R6, we also collected basal stalk samples, which are a good indicator of late season nitrogen status and potential excess nitrogen in the system. Grain was harvested using a 2-row plot combine, harvesting the middle 4 rows of each plot, and subsamples of both plant tissues and grain were dried to a constant weight, ground, and analyzed for total nitrogen content. To complement the plant data, we also collected soil samples at 3 different times: pre-treatment, V10, and post-harvest. These samples helped us track the dynamics of soil nitrogen throughout the season and at various depths. Samples at pre-treatment and post-harvest were taken using a Giddings increments, and V10 samples were taken using a hand probe. All soil samples were dried to a constant weight, ground, and then analyzed for nitrogen and nitrate and ammonia date and collected them promptly to avoid contamination or degradation. After collection, foams were extracted from pits shown in the pictures. Each plot has independent subsurface to take flow proportionate water. Says that flow weighted means that the values reflect not just the concentration, but how much drainage water actually flowed through the system on that day. So larger flow events have more influence, giving us a more realistic estimate of how much nitrate is moving through the subsurface. Needless to say, this project involved a lot of sampling and drainage. When on top of everything, and to make the most out of this project, I needed to be all in. So I moved down to Lamberton in my family's pickup camper so I could be near my study site. It wasn't fancy, but it kept me close to the plots, gave me full flexibility to monitor everything in real time, and it made me feel more connected to the work. It's conventional housing for a PhD student, but it sure got the job done. Now we'll go through some results and discussion. Here we have the weather data for 21, 22, and 23 growing seasons. On each graph, the blue bars represent daily precipitation, which is plotted on the left vertical axis. The black line is cumulative precipitation, and the green line is cumulative drainage, both of which are plotted on the right vertical axis. Both vertical axes are in millimeters. The horizontal axis runs from March through November, which captures the full drainage season for each year. Now, under more typical conditions, we'd expect cumulative precipitation and drainage to track closely at the beginning and the end of the season when the crop isn't using much water. But during peak growth and midsummer, evapotranspiration increases and we often see a divergence with more water being taken up by the crop. In 21, we received very little rain until August, which by that point the crop was already mature, so most of the water didn't do much to help grain yield. And because the soils were so dry, almost no drainage occurred, hence the nearly flat green line in 21. In 22, rainfall was again limited overall, but it was more timely. Most precipitation came early in the season when nitrogen fertilizer was applied and crop water demand was still low. This helped the crop take advantage of what little water there was, but drainage was still minimal. Then came 2023, which gave us so much precipitation in May that the plots actually ponded, as you can see in the photo. This year looked more normal with cumulative precipitation and drainage tracking closely together. So overall, 21 and 22 were extremely dry, two back-to-back drought years, followed by a season in 23 that was wetter, especially during critical drainage windows, but still had periods of drought. This meant that I ran a drainage-focused study during 3 years of drought, so you could say that my research was both dry and draining. This figure here shows grain yield response to nitrogen rate. The horizontal axis, we have nitrogen rate in kilograms of nitrogen per hectare, and on the vertical axis, we have grain yield in megagrams per hectare. Each year is shown with a different color, green for 21, red for 22, and blue for 23. The large dots represent the economic optimum nitrogen rate, or EONR, for each year, and this is the rate at where the value of the yield gain just offsets the cost of additional nitrogen. It's calculated based on the ratio of the price of corn to the price of nitrogen. In other words, it tells us a rate at which applying more nitrogen no longer pays off economically. You'll notice that 23 had the highest yield and the highest EONR, just over 10 megagrams per hectare, at the EONR of 209 kilograms of nitrogen per hectare, which reflects the more favorable weather conditions and higher crop responsiveness that year. In contrast, 21 and 22 had much lower yield responses and lower EONRs. What's interesting is that both of these years had a quadratic response, meaning that yields actually declined at the highest nitrogen rates. That's a bit unusual since we commonly expect to see a quadratic plateau response where the yields level off at a higher nitrogen rate, such as 2023. But in this case, drought conditions likely cause the decrease to happen at higher nitrogen rates. When water is limiting, the crop can't make use of the extra nitrogen, and sometimes too much nitrogen can even make things worse by increasing stress. It should also be noted that yields were affected by rootworm damage in 22, which likely contributed to the modest yield increase compared to 21, but the steeper rise in the EONR. So in the two driest years, applying more than 180 kilograms of nitrogen per hectare didn't help and actually hurt yields. This is very close to our mean EONR for the study of 173 kilograms of nitrogen per hectare. This reinforces the idea that nitrogen response is not just about how much you apply, but also when and how the crop can access it, which is often dictated by weather. This figure shows the relationship between how much nitrogen was applied above or below the EONR and the amount of soil total inorganic nitrogen from 0 to 90 centimeters. On the x-axis, we have the change in nitrogen applied, which is the amount of nitrogen applied above or below the EONR for that year. So 0 on the x-axis represents the EONR calculated for each year, and the vertical black line helps to show that. On the y-axis is soil total inorganic nitrogen in milligrams per kilogram. Red symbols represent post-harvest or fall samples. Blue symbols represent the following spring pre-treatment soil samples. The different shapes represent different years. And what stands out right away is that residual soil nitrogen measured post-harvest increased sharply when nitrogen applications exceeded the EONR. Fall total inorganic nitrogen rose linearly above this point, showing that once we pass the economically optimum rate, the crop doesn't take up the extra nitrogen efficiently. In contrast, spring total inorganic nitrogen levels were relatively flat across treatments, especially at or below the EONR, suggesting minimal carryover of soil nitrogen at those rates. Excuse me. The widening gap between fall and spring values at the higher nitrogen rates reflects overwinter losses, mostly through leaching and denitrification, or in drier years, some retention. That pattern was especially clear after 2022. Spring 2023 samples still showed relatively high total inorganic nitrogen, likely because there wasn't much overwinter precipitation to drive losses. If you remove 23, the spring trend line would be nearly flat, indicating that in most years, excess fall nitrogen doesn't carry over, it gets lost. The main point is that while both the fall and spring trend lines are linear, the gap between them grows with nitrogen rate, and that widening gap represents increasing risk. The closer you stay to the EONR, the smaller that gap is, and the less excess nitrogen you're leaving behind to potentially be lost. Now moving on to the nitrate leaching data, this figure shows cumulative area scaled nitrate leaching across the 5 nitrogen rate treatments. On the horizontal axis, we have nitrogen rate in kilograms of nitrogen per hectare, and on the vertical axis, we have cumulative nitrate leaching in kilograms of nitrate per hectare. Green bars represent 2021, red 22, and blue for 23. You'll notice right away that 23 dominates, especially at the higher nitrogen rates. At 180 kilograms of nitrogen per hectare and above, nitrate losses shot up sharply in 23, whereas in 21 and 22, the values remain relatively low regardless of nitrogen rate. So thinking back to our mean EONR of the study of 173 kilograms of nitrogen per hectare, we see that when you apply more than that, the losses start to increase rapidly. This makes sense given the differences in drainage across years. More drainage means more opportunity for nitrate to leach, and 2023 had both higher precipitation and higher drainage, especially early in the season when nitrogen fertilizer is most vulnerable to loss. This figure shows flow-weighted average nitrate concentrations in drainage water across nitrogen rates. Nitrogen rate is on the horizontal axis in kilograms of nitrogen per hectare, and flow-weighted nitrate concentrations is on the vertical axis in milligrams of nitrate per liter. Green bars represent 21, red is 22, and blue is 2023. This dashed black line is 10 at 10 milligrams per liter is the EPA drinking water standard for nitrate. Now, of course, agricultural drainage water isn't meant for drinking, but I'm just showing this line as a reference point to help put these numbers into context. The general trend here is that nitrogen rate increases, nitrate concentrations also increase, and we start to exceed that 10 milligrams per liter threshold right around 180 kilograms of nitrogen per hectare rate, which also happens to be close to the mean EONR. So again, at or below our EONR, nitrate concentrations mostly stay under or near the threshold, but once you go above that, you start to see more frequent exceedances. In 2023 especially, concentrations jumped quickly with higher nitrogen rates that reflects the combination of both excess nitrogen and greater drainage that year. Moving on to some conclusions. A flexible nitrogen application range is more practical than a fixed EONR. The mean EONR for our study was 173 kilograms of nitrogen per hectare, but year-to-year variability led us to calculate a coefficient of variation of 23%, which created an optimum range from 133 to 213 kilograms of nitrogen per hectare. Managing within this range allows growers to better balance productivity and environmental protection under variable weather rather than just using a fixed rate structure. Exceeding the EONR sharply increases environmental risk without agronomic gain. For instance, 25% above the mean EONR, grain yield only increased 3%, while total nitrogen losses jumped to 18%, primarily through nitrate leaching, highlighting little agronomic gain while increasing environmental risk. Now, one thing I really wanted to talk more about today when discussing nitrate leaching was how it interconnected with ammonia volatilization and nitrous oxide emissions. In our study, the dominant nitrogen loss pathway shifted depending on weather conditions. Dry conditions favored ammonia volatilization, especially when nitrogen was present near the soil surface. Isolated precipitation events triggered nitrous oxide emissions, and wet seasons where we had frequent precipitation events led to dominant nitrate leaching. I just want to highlight this because I couldn't show it today. When one loss mechanism increases, another one usually decreases, and depending on conditions and weather events, can be a significant amount of nitrogen lost in a small period of time. A special thanks to the Minnesota Corn Growers Association, USGS, Nutrient, and the Water Resources Center at the U of M. None of this research could have been done without your support. And thank you all for listening today. Does anybody have any questions?
Yeah, and as Shannon just put in the chat, if you guys are thinking of any questions, go ahead and put them in the Q&A box. While we're waiting for some of the questions to roll in, Zach, I was really interested, were there times of the year when, it was too cold and the ground froze and you weren't able to collect any water samples, or were you able to collect water samples and everything all year round?
Yeah, absolutely. So my pits actually have pumps in them that submerge in these pretty much garbage containers where the water drains into, and those pits will freeze right around like end of November, and then they'll thaw out like I would say end of March. So I have to take the pumps out so they don't break, and then I put them right back in as soon as like we think that they won't freeze and break again. And usually there's some ice down in the bottom of the trash can, so you got to get the ice out. If you don't wait for it to thaw, and then like as soon as you get those flushes, it's just kind of it's crazy when that snow melts happens. But like I said, and if you look at like my years, I didn't have crazy melting events other than I think it was 23. I had the most snow melt and drainage occur. So, yeah.
Yeah, it's always really interesting to see how, those weather conditions play into the nitrogen movement. And just like you said at the end with the volatilization.
Yep.
Still not seeing any other questions. Oh, maybe we just got one question in the chat. Okay, here you go. This one's from Kira. Hi, Zach. Your dedication and knowledge of the system is inspiring. What's your next step in this research? How could you use the information you found to advise farmers, or would you need to collect more information and give advice based on the season and precipitation?
Yeah, thanks for the question, Kira. And I know like our next step is kind of getting some things published and getting more of our research out there at conferences. I didn't really go into too much detail on all of our conclusions and stuff, but really just kind of getting this information out there and then also putting all of our nitrogen rate data, all the stuff we learned with our EONRs kind of into the Minnesota State database is going to be the best place for our kind of data. But we definitely need to know about the season and precipitation, and that's kind of what I was getting at with that range there at the end. If you can kind of guesstimate if it's going to be a wet or dry year, that's kind of using this data that we've collected to advise that choice of a nitrogen rate that you should go with. But yeah. Um,
Yeah, I think let's go ahead and take this next question. And then if you have other questions for Zach, go ahead and put them in the chat and I'll have him type them because we'll need to get on to our next speaker. But this one, I may have missed this, but did you monitor any other nutrients in the water samples? Also, love the dedication to collecting as many samples as possible. Major kudos.
Thanks, Austin. Um, yeah, so we did measure phosphorus, bray, and then ammonium. We actually haven't published that data yet, but we've kind of discussed looking at it. I do know just glancing at the data that phosphorus is very low and usually not readable, but or measurable. But I have seen a like maybe one or two numbers. So we might publish the data just to let everybody know what's kind of out there because we have the drainage data collected all the way previously before me too. So like back from 2014, I think has been this system. So and then ISCO's before that. So yeah, I think you're
Okay,
right.
thanks again. Thanks again, Dr. Honorud.
Thanks.
And yeah, again, if you have other questions for him, feel free to put them in the chat. But now I will introduce our next speaker, Dr. Shangnang Zhou. Dr. Shangnan Zhou is a senior research scientist of the Soils Lab at the University of Illinois Urbana-Champaign. Dr. Zhou studies the transport, transformation, and storage of sediments and nutrients in the stream banks, floodplains, and streambeds in river systems and their impacts on water quality. Dr. Zhou is leading a research effort to quantify the Illinois statewide stream bank erosion and phosphorus loss to inform effective nutrient loss reduction strategies. Today, Dr. Zhou will be speaking about the hidden enemy, how stream bank erosion contributes to phosphorus pollution. So take it away.
Okay, then thank you, Lizzie, for the introduction. Um, um, Hello, everyone. I'm very happy to be here. My name is Shannon. Today, I'm going to talk about the hidden enemy, which is how stream bank erosion contributes to the phosphorus loading. So, excess phosphorus export from the Mississippi River Basin have been linked to the hypoxia in the Gulf of Mexico, which is the second largest hypoxia zone caused by human impact. And then in 2012, across the whole Mississippi River Basin, the total P yields was averaged at 79 kilograms per square kilometers per year. And then the top yields are coming from the Upper Mississippi River Basin, Ohio Sub-Basin, and the Lower Mississippi River Basin. For Upper Mississippi River Basin particularly, it has extremely high total P yields with the average amount of 132 kilograms per square kilometers per year. So to reduce the hypoxia zone to an acceptable size, the US EPA hypoxia task force have set the interim target to reduce total P loading from Mississippi River Basin by 20% from 2012 to 2025. But now this timeline has been extended to 2035. So in order to establish an effective, cost-effective neutron loss reduction strategy, it is important to know where to concentrate on the management effort, and also to know where to aim the conservation and the restoration management practices, which means we need to know the source of the P loading. So in the Mississippi River Basin, there are 4 key sources of phosphorus losses, which is fertilizer, manure. These are agriculture related, the wastewater treatment, and then laterally about stream banks or in-stream channels. So here we all know for wastewater treatment as a point source, manure or fertilizer, and stream banks, they are long point source. But in the last decade, good effort and progress have been made to reduce P loading from point source and then agriculture runoff. But however, little effort or progress has been made to reduce P loading from stream bank erosion. As you can see here, actually, stream bank erosion or in-stream channels can contribute 22.7% of the P loading in the Mississippi River Basin. This is because low state in the Mississippi River Basin has accounted for stream bank erosion in their neutron loss reduction strategies. For example, in Illinois in 2014, their neutron loss reduction strategy, they categorized the P loss sources into three types, which is runoff, 4% point sources, 48%, and then agriculture, 48%. This means they lumped the stream bank erosion sources into agriculture, but we know agriculture doesn't exactly equivalent to long point sources. So it's very important to know what are the agriculture versus stream bank sources in the long point sector. By not distinguish the P loading from stream bank erosion versus agriculture, the P contribution from agriculture would be overestimated. That one could lead potential manageable long point source of P is missed in strategies to reduce P nodes, and also neutron loss reduction resources may be disdirected because they're not targeting those hotspots. For example, the stream banks, somewhere their hotspots could be missed. And then lastly, the total P reduction goals by 20%. This expectation may not be realistic. So stream bank erosion is a very important non-point, non-agricultural sources of P loading to streams. Stream bank erosion usually happens when the toe of the bank is scoured by the stream flow, which led to the upper part of the bank overhang without a solid foundation. With time, the overhang upper part of the stream bank will collapse due to gravity. Through this process, the sediment-bonded phosphorus will enter the stream, and then the phosphorus usually enter the water column by desorption. This process will increase the phosphorus concentration in stream. So through this process, stream bank erosion contributes significantly to river P export. So in order to quantitatively know how much stream bank erosion contributes watershed export, P export, we conducted a systematic literature review and meta-analysis. We collected 1,079 reports from 163 peer-reviewed articles, and then this map shows the spatial distribution of those stream bank P loading reports. Majority of them, they focus on the US, but we see a lot of studies they have taken place in the Midwest and the east part of the US. So globally overall, the total phosphorus load from stream bank erosion is averaged at 1.5 kilograms per hectare per year through this meta-analysis. And also we found that the stream bank erosion can contribute an average of 30%, 31% of watershed P export. So among those records, a substantial amount of studies taken place in the Mississippi River Basin, typically in Minnesota, Iowa, Illinois, Indiana, Missouri, and Oklahoma. So in those studied states, but they are all watershed scale though, stream bank erosion contributes 3% up to 7% to the P loading. And then we found that not only the total P loading is overlooked, but also the form of the phosphorus in the stream bank soil is also overlooked because the phosphorus in the stream bank soil exists in different forms. The different forms of phosphorus have different P releasing rate that could indicate their time scales on the impact of water quality. For example, in this diagram, we showed the 5 types of phosphorus: soluble phosphorus, organic phosphorus, iron bonded phosphorus, apatite phosphorus, and residual phosphorus. And then they have different water solubility. For example, soluble phosphorus can be released into water immediately for algae uptake. And then, but for iron and phosphorus bonded on iron oxides or apatite minerals, they're more difficult to be dissolved. It can take years or decades for them to be released into water for algae to use. So, but only we found that through this pie chart, you can find roughly only 3% of the total P is soluble phosphorus. But this small amount of phosphorus, they can make a disproportional high impact on water quality because their effect is immediate. But then we also don't forget the legacy effect of those large quantity of phosphorus. Once they are eroded into the stream, they are stored on the bed. They kind of release phosphorus very slowly as a DRP slowly. So it may take decades, even to centuries, for them to see to impact the water quality. This could lead the lag times between the P reduction practices and the water quality improvement. So our recent study in the Pocket watershed in the southern Illinois also found the high variability of P pools across the stream bank profile, which entails the different degree of impacts on water present or versus future water quality. For example, on the left side of this figure, it shows 5 P profile, 5 vertical distribution of phosphorus pools at 5 stream bank profiles. Overall, it showed that the soluble or organic phosphorus were dominant pools of P in the upper part of the bank. Usually the A horizon, it can take combined, it can take around like almost up to 50%. But this phosphorus, they have faster releasing rate, so they could impact the water quality immediately. So that indicates if the upper part of the bank is eroded, that phosphorus will impact the water quality at a shorter time scale. But on the other hand, as you can see, the orange color and the purple color, they are calcium bound phosphorus or residual phosphorus. They have very low releasing rate, and then that means if the lower part of the bank is eroded, their impact to water quality will have a longer time scale. So in order for each state to develop a realistic nutrient loss reduction strategy, it's very important to know how much phosphorus exported from each state is actually contributed by the stream bank erosion. So in the Mississippi River Basin, all the states so far, only Iowa State did that. So a recent study showed that in Iowa, about 31% of total phosphorus exported from Iowa State into the Mississippi River Basin is coming from stream bank erosion. So as a neighboring state, Illinois, however, current doesn't have any even crude estimate of total phosphorus contribution from stream bank erosion. So our ongoing project right now is to fill this gap to quantify stream bank erosion contribution to P losses in Illinois. We're using erosion pins to achieve this. So in this map, those red dots are the erosion pin sites. We installed erosion pins across the whole state of Illinois, basically in 908 watershed that represent the major land resource area. So the erosion pins is a very simple tool. It's basically a 2 feet long, 1/4 inch thick rebar. We insert the rebar into the bank perpendicularly as the stream bank starts to retreat, and the rebar will progressively expose. So that length, we measure that exposure length every 6 months to determine the bank recession rate. We also collect soil samples across the stream bank profile showing on the right side figure. We take the soil sample to the lab to analyze total phosphorus concentration and the bulk density. That could help us to calculate the total phosphorus loading from stream bank erosion. So far we have installed 2,375 erosion pins along 475 stream reaches across the whole state of Illinois. It took almost more than 3 years for us to do that. And then we found that in this map, it showed the spatial distribution of stream bank recession rate across the state. We found that the higher bank erosion appeared at the north part and the southern part of Illinois. This could be related to the topography, because in the north and the southern part, we have hilly landscape. The topography, the slope is steeper. The water could have a higher erosive energy to erode the stream bank. But on the other hand, in the center part, you see have lower recession rate. This is because in the center part, mostly are flat, where we Champaign here located are relatively flat. We got a lot of meandering rivers. That the water could have lower energy to erode the banks. So overall, across the whole state of Illinois, the average bank recession rate so far as the 3-year low measurement is 3.3 inches per year. And then the average sediment loading from stream bank erosion across the whole state is about 229 pounds per feet per year. All this together leads to about 0.05 pounds phosphorus loading to the stream per feet per year. So this led to my conclusion. So on my talk today. So far, the long point source P loss in the Mississippi River Basin have not quantified contributions from the long point sources, for example, stream bank erosion. And then we know stream bank erosion is a key significant source of P loading, but it has been overlooked. So I think in order to develop a more cost-effective nutrient loss reduction strategy, it's important to account for stream bank erosion. But unfortunately, most of the states and the Mississippi River Basin currently do not account for stream bank erosion. This is because stream bank erosion is extremely hard to monitor, to quantify. And then we also know only a small fraction of phosphorus accumulated in the stream bank soil can be released as DRP immediately. For example, the exchangeable phosphorus. The majority of phosphorus are associated with the calcium, and then those minerals, they are more difficult to dissolve, and then they can release to the water for years or decades. This could lead to the legacy effect of phosphorus in the stream. So it's important to account for the legacy effect on the time lags for water quality recovery to establish the realistic expectations of nutrient loss reduction magnitudes and timeline. Thank you. Happy to take any questions.
All right. I think looks like we have time for one question, and then I'll have you answer the rest of them offline. And of course, if anybody else has any, please feel free to put them in the chat. The first question that came in is, how often do you guys lose the erosion pins, or do they usually stay where they're placed?
Sorry, could you please repeat the question?
Yeah, sure. Those erosion pins that you're currently using, in the stream banks to measure the erosion, do you lose those in the field, due to the erosion being more than you think, or did they stay in place?
That's a good question. We do have a lot of pins they got lost. That's majority of them they are lost at basically the mass failure. When there is a mass failure happens, so the user pins got lost. So we got the metal detector when we visit the site, we get metal detector to find the sites. We also lost some pins because some people just removed it. I don't know. We have pins lost. Yeah, but we are trying to find and recover those pins. Yeah, we revisit the sites.
Great. Well, we'll have to move on to Gabe, but thanks again, Dr. Zhou, and answer the rest of those questions next. And I will go ahead and introduce our final speaker here. Our final speaker is Dr. Gabe Johnson. And Dr. Gabe Johnson is a postdoctoral research associate at Iowa State University, where he recently completed his PhD in agricultural and biosystems engineering and sustainable agriculture. His current research focuses on assessing the performance and function of saturated buffers for removing nitrate from agricultural drainage. The objective of this work is to improve design guidance for saturated buffers to support progress towards state and regional nutrient reduction goals. Inspired by his experiences growing up near the Mississippi River and visits to his grandparents' farm, Gabe's broader goals are to develop solutions to improve water quality and agricultural sustainability. Today, he will be speaking about improving saturated riparian buffer design and nitrate removal performance, insights from new monitoring data. Take it away, Gabe.
All right, thank you very much. Happy to be presenting here today, along with these other great presenters from the Upper Basin. As Lindsay said, my name is Gabe Johnson. I finished my PhD this past spring at Iowa State, and I'm continuing to work at Iowa State as a postdoc, working on water quality, especially with nitrate in our corn soybean production systems here. So my presentation will focus on some work from my dissertation and then kind of additional work, kind of where that's heading into my postdoc. So just a brief introduction. I think most of us on this call are familiar with the water quality challenges in the Mississippi River Basin. And so where I'm at, where I've done my research here in Iowa, is a part of the basin that has a very intensive agricultural production, specifically with corn and soybeans, and that is supported by a lot of artificial subsurface tile drainage. And we heard Zach's presentation earlier on those plot studies with nitrate and the cropping systems. We have a lot of tile drainage here in Iowa. I have circled on that one graphic. You can see across much of the Corn Belt. And so that leads to water quality challenges with lots of nitrate losses. This year in particular was a particularly bad year in Iowa for nitrate loss. And so that's one of our big challenges is the nitrate loss through our tile drainage. And so one of our tools that we can use to work on that problem is an edge of field conservation practice called a saturated riparian buffer, or a saturated buffer. And what this is a conservation practice that utilizes the naturally occurring capability of a riparian buffer to remove nitrate. And so, with those tile drainage systems, those tile drainage systems would otherwise bypass a riparian buffer. And so what the saturated buffer does is it allows us to reconnect that hydrology. What we do is for this practice, you go in and you put in a water control structure on that tile line, and then you put in an additional perforated pipe that runs parallel to the stream, and you use that as this distribution line to redistribute some of that drainage water and allow it to percolate and flow through the soil of the buffer, and you get denitrification, converting that nitrate into nitrogen gas. You get plant uptake of the nitrate. And so this is a common practice now being implemented across Iowa and across other parts of the Midwest. And so overall, we know that saturated buffers work pretty well compared to some of these other edge of field conservation practices. In a literature review I led, we reported that the typical attritional design averages around 46% removal, or about 9.4 kilograms per hectare drained. So overall, we know kind of that baseline, we know a general range. Here's the average of how well they work, but how can we make these work better? And that's what a lot of my dissertation research focused on. And so I looked at how do alternative management and alternative designs affect performance. And then I looked at how can we improve designs and improve the design methods with some empirical performance data. And so that's what I'll be focusing on today and talking about a little bit more. So one key feature of saturated buffers I want to highlight first, though, is that this practice does not treat all of the drainage water. So unlike say a wetland, which may capture all of the flow into it, a saturated buffer is designed to bypass high flows because there's only a certain treatment capacity of that riparian buffer, of those soils, of the distribution pipe. And so these are designed to bypass high flows so that the drainage system still effectively drains for those agricultural producers. And so because of that, that is a limitation to how well the practice works. Generally, of the water that is sent into the distribution pipe and moved through the buffer, we see really high removal, generally upwards of 80%. On average, about 82% of that nitrate is removed as it moves through the buffer. And so that actual fraction of the flow that we treat, what is treated, what is bypassed, is often one of our main limiting factors to the overall performance. And so that 46% removal on this slide, that includes that bypass flow. So motivation for this study specifically is focusing on some of the design criteria for saturated buffers. And so the efficacy of the current design criteria has not been assessed yet. So the NRCS has the conservation practice standard for saturated buffers, code 604. And what this states is that the saturated buffer should be designed to be large enough to treat 5% of the drainage of the peak flow from the drainage system, or as much as possible based on what is available. Right. So as I put in that equation form there, flow through the saturated buffer should be at least 5% of that peak. And so that is in that NRCS standard. And then that goes into the saturated buffer design spreadsheet that is used to perform the calculations to size the length of the saturated buffer, the width, and some of the other design criteria. But we know that our mass load removal is going to be driving our total water quality improvement overall. And so there could potentially be a disconnect between a percentage efficiency compared to a mass load removal. And so the question with this is, does that percent of peak flow method really create good designs for mass load removal as opposed to the efficiency? Because we think, the more flow we can treat, the more efficient that saturated buffer will be and should have more mass load removal. So objectives. One objective for this study was to report data for additional site years. That kind of gets incorporated into these next two objectives. So what I'm going to focus on for the next few minutes are assessing those design parameters against the actual observed empirical nitrate load removal, and then how we are using that moving forward to suggest some alternative design methods. So brief methods on this study. For this, I used 5 saturated buffer sites with a total of 44 site years between 2011 and 2024, with some different years for each site, depending on when it was installed. These different saturated buffer sites had a range of design characteristics with drainage areas, distribution pipe lengths, the saturated hydraulic conductivity of the soil, and some of the other parameters. Overall, the saturated buffers were similar in width, and 3 to 4 of them of the 5 were pretty similar in drainage area, and we had one with a really large drainage area. And then I retrieved some of those design criteria characteristics from the NRSys design spreadsheet for each practice, and then I used a linear regression analysis to look at some of the predictor variables for the nitrate load removal and explanatory variables. So briefly, monitoring at these sites, we monitor for two key things, flow and nitrate concentration, because that is what allows us to quantify nitrate loading. And so for flow, we measure both the total drainage flow from the tile and then the amount of flow that is treated and diverted into the saturated buffer. We do that using these V-notch weirs that are located in these water control structures on each site. And then for nitrate concentration, we install arrays, transects of monitoring wells across the buffer, with wells kind of generally about equally spaced from the distribution line towards the stream across the buffer. And so from there, we collect water samples, and those go back to the lab, and we analyze those for nitrate and can quantify nitrate loading when we put that with the flow data. Okay, so jumping into the results, big kind of first key takeaway, key result from this study was that our mass load removal was highest at the site with the largest drainage area. So that's this BC2 site circled over here on the right. Overall, this isn't too surprising of a result. And I'll show a slide. The next slide will show kind of total nitrate load inputs as well as what's removed. But this makes sense when we think about the larger the drainage area, the larger potential inputs, and so the larger potential, inputs that could be removed. Now, when we looked at the efficiency, so the edge of field nitrate removal efficiency, that accounts for the bypass flow. And so this was highest at a site with a relatively small drainage area and a long distribution pipe length. So that's this IA1 site, circled right there. Really high efficiency. This site treated generally upwards of 80% of the flow, and then had upwards of the 80% removal within the buffer, and so that resulted in that very high total efficiency at the site. But you'll notice that the actual mass load removal was about in the middle across all the sites. So as I said, when we look at both total load from that drainage area and then what is diverted and removed, that kind of provides us with a little bit bigger picture, more to the story. And so you can see at that BC2 site with that largest drainage area, the mass load inputs coming out of that tile were the highest compared to the other sites, which is what allowed that total load removal to be higher, even though that efficiency is lower at that site, simply because more of that drainage flow is bypassed. And in comparison, that IA1 site, you can see that what was removed in the buffer very similar to total load from the field. So we looked at regression analysis. The key things we saw here. So this figure on the left, this is plotting the that percent of flow treatment from design. So this is the design criteria. The design standard calls for this to be 5%. None of these sites met that 5%. So these range from about 0.3% to 3%. And then mass load removal is on the y-axis. And so there was really a very weak negative trend in this, which seems to indicate that at some of these sites with that larger percent of peak flow treated by the saturated buffer, these may be the sites that have smaller drainage areas. So that saturated buffer can be more efficient, but may not necessarily have the highest mass load removal. And then this figure on the right is a little bit maybe funkier looking with the design parameters that go into this, but this is plotting mass load removed against this combination factor that includes the drainage area, the saturated buffer distribution pipe length, the precipitation, and the flow weighted mean or the flow weighted average concentration. And so what this is showing is really those four factors are kind of accounting for a larger set of factors, both representing the potential inputs of nitrate from the field, from that field tile, and then what can be removed by the saturated buffer based on that length of pipe. And so as we increase the drainage area, the pipe length, precipitation concentration, potential for greater load to be removed in the saturated buffer. And so that is something we think we can use moving forward in a modified design spreadsheet. We think this could be incorporated to estimate mass load removal across a potential, at a potential new site based on some of those design characteristics and an estimate for precipitation or concentration. And this could then be used to compare and rank sites based upon not only mass, so not only that percent efficiency, like the current design spreadsheet, but also on that mass load removal, because we know that will be really driving our goals, and that will be impacting our cost efficiency as well when we think about $1 per kilogram or $1 per pound removed. And so some key takeaways and limitations with this work. Saturated buffers the design should prioritize sites with larger drainage areas and really maximizing that distribution pipe length to maximize the nitrate load removal. And what this work really showed is that the percent efficiency doesn't necessarily equate to mass load removal because of those differences in inputs. You could have the same saturated buffer design characteristics that are placed on two different drainage systems, and you would have different results for mass load removal and efficiency for that saturated buffer. And so because we know that the saturated buffer length and the flow through the saturated buffer is going to be limited by the site, that percent of peak flow method may be guiding us towards some of those smaller drainage areas and lower loading sites that are more efficient. But maybe we should be thinking about those larger area sites that will have greater load, greater potential to remove that load. And briefly, some limitations with these 5 sites. We still didn't have the largest set of different design characteristics for the saturated buffers. So we're working on adding additional sites to this analysis that have different sizes of drainage areas, different widths for that distribution line, some different soils, because we know all of those will impact the saturated buffer performance as well. And then last thing, as I wrap up here, I think I'm just going to jump through these next steps. The next thing we're looking at is actually comparing the observed flow through the saturated buffer, that observed performance, with our design prediction, and seeing how we can use that data to also improve the designs. And so with that, I'll acknowledge so much support on this project during my PhD. Tom Eisenhart is my co-author and my co-advisor, along with Michelle Sapir. Great collaborators, and of course, this work is always, you need your everyone helping out in the field and in the lab to get that done. And so I know we've approached 1 o'clock, and so if we have a chance for a question or two, I'd be happy to answer it. Thank you.
Great. Yeah. Thanks, Gabe. And since we are recording, I don't know, Shannon, is it okay if we answer a question or yeah. That way people have to leave. But yeah. We do have a question in chat, and feel free to type any other chats questions here if you guys are still in the Zoom. Assuming denitrification is responsible for the removal, have y'all quantified N2O productions? Is the question we have.
Yeah, that's a great question. So there was a study maybe 6 years ago, prior PhD student with my advisor who's now at Missouri, Morgan Davis and Tyler, two folks, Morgan Davis and Tyler Grow looked at uh, in situ denitrification. They looked at nitrous oxide, some of the greenhouse gases, and what they found was that denitrification was the largest sink that they were seeing at the saturated buffers. Um, and I think the nitrous oxide production was pretty low. But yeah, that was one study, and that included, I think, about three saturated buffer sites. Um, but besides that, not a ton of work on some of those other on the greenhouse gases.
Great. I think that's all we had in the chat. So thanks again, Gabe, for presenting. And I'll turn it back over to Shannon just for a couple closing comments.
Yes. I just want to give a shout out to our three wonderful speakers. Thank you so much for spending time with us today and everybody who attended and showed up. I dropped a reminder in the chat that don't forget, we have two more seminars in this series, one focused on the Middle Basin on October 20th and then the Lower Basin on November 3rd. There's a link in the chat as well to sign up, and then stay tuned for those details on the early career seminar or workshop. And with that, that's it. So thank you, everybody. We're so glad to have had you, and we'll be circulating and recording as well. So thanks.